Thank you. Thank you. It's lovely to be back at the JLF. And we're going to try and give you a sort of a bit of background. And we want to show you some real examples of these digital twins, because it sounds a bit science fiction, but these things are real. But maybe just a little bit about background. We've done 3 books together, and since 1990, crikey, it goes back a long way, where with the Hour of Time, we were looking at the laws of physics and looking at a contradiction of the laws of physics. They don't really accept that there's an hour of time. Then we looked at Frontiers of Complexity, complexity theory, and how computers can help you model the messiness, mesoscale messiness. It's easy to model the subatomic world, easy to model the universe. The bit in the middle where we live is difficult. And then finally, Virtual You, where we're talking about digital twins of people. I mean, have I captured it, Peter?
Absolutely perfectly, yes.
Thank you. Phew. There we are. I do know what I've written, actually. So for us, what's kind of totemic about digital twins is they're already kind of out there being used. Now, engineers talk a lot about digital twins, but we think the one that really maps onto the digital twins we're going to talk about in medicine are these forecasts of things like hurricanes, climate modeling, and so on, where, I mean, Peter, give the audience a sense of what it takes to forecast a hurricane and sort of say, look, we've got to evacuate Miami or whatever.
Are you talking about in terms of the computational resources?
Yeah, exactly.
So just about everything we talk about here involves supercomputers of a considerable power. The most performant ones are in the exascale, which means 10 to the 18 floating point numbers per second. So,
and there are only a few of those big beasts on the planet.
At the moment, only 3 have got that label against them, but all the weather forecasting offices and services in the world that are worth anything will have a very powerful supercomputer, because what they're trying to do is predict the future before it happens, as opposed to retrodict it after the event. And that's what we're trying to do in a case like this. Today, for disaster prediction, it's quite possible to predict from the onset of a hurricane several days ahead where it's going to evolve, where it's going to hit land, what it'll do once it hits land. And obviously, these predictions are very powerful because they can avoid deaths and damage to property if they're reliable. They have to be accurate. And the digital twin element that you mentioned is more than just the simulation. In the end, it's actively looking at how the object, in this case it's part of the world, is evolving compared with your own simulation.
So we've got basically, to produce these predictions, you've got a computer model which captures the mathematics of the way that the atmosphere works. And that's resting on billions of equations, literally billions of equations. And then you've got to put in data, so satellite measurements, buoys, weather stations, they're all feeding information into this model, and then it's cranking out this prediction of what's going to happen in a few days' time. So the whole premise of Virtual You and digital twins in medicine is to basically make health casts rather than forecasts, so using exactly the same approach that we're using now for weather forecasting in the medical sphere. So let's have a look at one. So here's a really common example. So you're sort of thinking, crikey, this is some weird abstract art. But in fact, what we've got here is an anti-cancer drug, which is the kind of shiny balls, and it's shown binding to an enzyme. Peter, talk through the promise of how we're using digital twins already to develop new drugs and so on.
So the message is we have to understand the phenomena sufficiently well that we can make a forecast with a powerful machine ahead of an event, so that we can then turn it into an actionable prediction, meaning someone believes what we're saying and does something as a result, such as evading or getting people away from the eye of the storm when there's a hurricane going.
Yeah.
Here we're trying to deal, typically in the most urgent cases, it could be an infectious disease, COVID being one, HIV, where you're up against an individual who needs treatment and they're facing a mutating enzyme which it's going to interact with, a protein. So the issue is, how quickly can we get the patient's personal, let's say the protein, so that revolves around the sequencing of the let's say the virus that's infecting the individual, and what drugs we have available that will fit in. So we have to do a lot of computations very quickly to make a prediction within a matter of hours to days to say what drug this patient should use.
And you've actually done this, haven't you? So you've had a study in the Middle East where there were women. So basically, we've all got slightly different proteins in our bodies. So you want to pick the right drug to hit the right protein. So what Peter did was you studied a population of women, you looked at the differences in the protein target, and then you could figure out which anti-cancer drug
to pick, yes.
To pick.
Sometimes you do discover new mutations. That was a study with women suffering from breast cancer in Qatar, incidentally, that you're thinking of. But currently we have other work on the go with tuberculosis. The interesting thing about these cases is when it's a pathogen like a bacterium or a virus, we're not talking about genome sequencing of the whole patient. It's simply that component of the pathogen that's spliced inside your genome.
Right.
It's much shorter, but it's the thing that carries all the information about the sequence of that particular pathogen and whether it's got mutations. And then, indeed, if you can run these computations fast enough, you come out with a prediction as to which of the potential inhibitors available will work for some patients and which for others. It's analogous to the weather forecasting.
Let's show you another example now. So here's a virtual breath developed at Imperial College by Dennis Dawley and also a team at the Barcelona Supercomputing Center. And here you can see how, for example, if you're interested in someone taking an anti-asthma medication and how that medication is deposited in the lungs and airways, you can use this sort of model to do that work, can't you, Peter?
Absolutely. What you need is imaging in this case that represents the individual. The images that are taken of all of the pathway down into the lungs, and then you would run what we call a CFD, or computational fluid dynamics simulation, which is showing where these aerosol sprays will end up. So that one's closer to a weather forecast because CFD, or computational fluid dynamics, is a common play in
Right.
both. But this is a patient-specific case. Now it's the image data of the individual patient against which you run the simulation.
But there are even more digital twins of patients out there. So let me give you another one, if I can. So there was a lot of interest. I mean, actually, one of the staggering things about COVID was it took a surprisingly long time for people to realize that it was aerosols that was moving the virus around. There was a lot of obsession with cleaning surfaces. I mean, that is important as well. But of course, there were these amazing studies, particularly in actually South Korea, where they could track people's movements using their mobile phones. You could see how someone with COVID in a restaurant infected someone sitting a few tables away because the aircon was taking the aerosol from around their table and maybe moving it further into the restaurant and so on. But that's one very vivid example.
Again, that's another example with computational fluid dynamics underpinning it, the science of how fluids and suspensions move under flow conditions.
And of course, we've got the corollary of this, which is we don't often think about them as digital twins, but those models used to predict how the pandemic would sweep around the planet, they again were trying to simulate properties of the population and how the virus moves. Now, I know some of these things have been controversial, but I would still say that I'd rather have someone doing a digital twin that is giving you insights into how to control the virus than a prime minister making it up as they go along. So I still think models have got a lot of value. I mean, I don't know what your take on these is, Peter.
But to come back to the digital twin aspect of this, historically there's a trend to do a simulation in a certain static way of phenomena that you're trying to handle. The digital
Right.
twin concept is I must keep that up close and personal in a way to the real entity, in this case it's all this data about disease propagation, but it could be on a human. And we need to keep the two things consistent with one another. So that gives you checks on whether your simulations are correct. It gives you more data to correct them, but also the forward-looking nature of the simulations, if they're run fast enough, tells someone who's typically a physician in our case, what to do next. If they have enough faith in what the predictions are, they can take actionable decisions, say, to prevent more deaths occurring.
Yeah, and of course it was modelling like this that showed a team at Imperial that actually lockdown seemed the only option in March of 2020 to deal with the virus. Obviously things got much more complicated after that. So here's a more straightforward example of a digital twin done by Marco Vicaconti, who was at Sheffield, and he's now moved
back
on.
in Bologna in Italy. Yeah.
But you can see now how the stresses and strains on hips, you could simulate the forces on an elderly pelvis to look at things like osteoporosis, bone weakening and so on, to try to get a bit of insight there. So this is quite a straightforward use of digital twins.
So it's trying to predict the potential of a fracture developing and preventing it from occurring before it does.
Exactly. And now here's by Michelle Oyen. This is the uterus and actually looking at caesarean operations. And what's interesting is that, doctors discover by trial and error over many decades the way to do a caesarean. And to put it simply, you can either do a vertical cut or a horizontal cut. And what she found with digital twin modeling was actually you've got a much higher risk of a rupture after the operation if you do a vertical cut than a horizontal cut. So you can sort of get a bit of insight into why surgeons have found horizontal is the best way to go. But equally, if you've got a patient with a particular abnormality, you can use this digital twin model just to check that's the right way to do the operation. So again, a very practical use, isn't it, Peter?
And maybe we haven't emphasized yet enough that we're talking about personalized medicine now.
Yeah.
We're treating each person on the basis of their data. And I know something is lurking around the corner here, because some people might be saying, are you talking about AI? The answer is, no, we're not at all at this moment. We're talking about data for you as an individual being used to predict what's going to happen to you. Artificial intelligence in general isn't doing that. It's taking a huge amount of data on other people and having the temerity to tell you how you will respond. Yeah. And the challenge is to be sure that the statistics of the individual have anything to do with you. And for example, in India, we're not there, but we gave this a discussion like this there. I was in India for the whole of January, and I spent quite a bit of time with one of the leading private healthcare companies there. The concern they have is, and it's quite surprising to many, that the data we have to go on to predict things in other parts of the world than the Western one is Western human clinical trial data, etc. When you understand the incredible heterogeneity, variety of people in the Indian subcontinent, and you think you can make predictions of how they're going to fare based mainly on white Caucasian males, it's a bit of a joke. So we can do a lot better, and this is the way we're trying to advocate. That's why in India they're particularly interested in a digital twin model.
And in fact, there's one thing we should sort of stress about the vision behind Virtual You, which is that modern medicine's rather strange in several ways. So your GP never really makes a prediction unless you've got something really severe, like a bullet through the head or something. It's quite hard for them to know how you're going to predict how you're going to react to a drug. I've lost count of the number of times that a doctor has said to me, try this medicine, and if it doesn't work in 3 weeks' time, we'll give you a different one. Well, this approach is trying to actually stop you being experimented on, and actually you should do that experiment on your digital twin. So the weird thing about contemporary medicine is it's backward looking. It's based on trials done on patients who really might be a bit like you, or they might not be a bit like you in the past. It's not predictive and it's not personalized. It's one-size-fits-all medicine. Strikingly, a lot of very common drugs only work for about half the people they're given to. We often angst about side effects. There probably should be as much angst about the fact that a lot of people just don't respond to a particular drug, and that wastes valuable time.
And that comes back to the central goal of the pharma industry today, which is usually to make a one-size-fits-all drug. They don't want to be trying to look at diversity because it's hard enough to make one drug. It takes 10 years, around $2 billion. Only 4% of the projects which are initiated lead to success. And when they're successful, they usually only work for about 50% of the population. Scientifically, we can do a whole lot better than that, but it requires much more sophisticated use of information technology, including the kinds of things we're discussing here.
Exactly. Let's go to another digital twin. Now this one's a bit more, obviously the Everest of simulating the body is the brain. And the brain is the most complex known thing in the universe. And of course we wouldn't go as far as to claim that you can simulate in any big meaningful way the brain. But you can capture certain qualities of it. So this is looking at the connectivity of different regions of the brain. And it's part of a trial done in France on patients with very severe epilepsy. And when the drugs don't work, you have to do an operation to remove the bit of the brain that's triggering seizures across the brain. But of course, you don't want to remove some important brain tissue. So what they do is they come up, they measure on a patient-by-patient basis the connectivity of key brain regions, just as a double check that when they do this rather drastic last resort surgery, it doesn't actually have an unfortunate consequence. So it shows that even with the brain, we're beginning to see digital twins being used.
Totally, yes.
And in fact, Peter, what do you reckon are I mean, we've now got amazing models of like a cubic millimeter of mouse brain and things like that. Do you think, how far do you think we can get in the next sort of 10 years or so in simulating more of the brain?
The big mistake is to assume, as quite a lot of medics and biologists do, that we have to understand everything in every minuscule piece of detail down to the molecules and proteins and so on that are causing mechanisms to occur in the brain. But the message of, let's say, the physics-based approach, trying to understand how complex systems develop, is that it's never necessary to include everything. Because if you try to do that, you will never actually get anything going in any computer.
Yeah.
Depends on the type of, in this case, medical pathology you're interested in, what scales you're concerned with. So some of the things we do relate to, could be important things like strokes and aneurysms that people have in their brains. That's purely determined, let's say, at a very high degree of, good approximation, just by the structure of the arteries and veins that are present, what we call the intracranial vasculature. You can get that from imaging. If you can then run fluid dynamics simulations, as we were talking about earlier, of the blood and what's constricting it and so on, it's a combination again of imaging, which is available today, and the fluid dynamics simulation we talk about, and we're already addressing some problems in the brain. Often in these type of events, someone comes up to us afterwards and says, yes, but can you model, the mental state of an individual, because that can affect a medical treatment, and that's certainly possible. We know that happens, but we're making no claim at the moment that science understands enough about that to usefully intervene. But the purpose of digital twins is to have models and experiment and eventually achieve convergence between them. This is a huge area, both for immediate action and for the future direction of medical research.
Yeah, and I think actually I'd like to give you a kind of analogy. We use this term model, which is basically a bunch of maths that you run in a computer. A lot of these things we've shown you look like the real thing, but the point is they behave like the real thing as well. But let me give you an example of where a model can be useful, but it doesn't have to be accurate, because you probably used it today. If you want to navigate around London, I could give you a satellite image of London at low resolution, and you might think that actually if I give you another satellite image at ultra high resolution, down to the last foot, that you should find it easier to navigate around London. But I can give you a simplified model of London. It's called a tube map. It's not accurate at all, but it's really useful. It actually can pretty much get you from A to B without data overload and so on. So in a similar way, the digital twins, we've shown you some that look like the real thing, that behave like the real thing. Some of them are quite abstract, but rather like the tube map, they can still give you insights into the way the body works.
Can I just add in another thing there? Because you said models, a large amount of mathematics that then is put into a computer program. That's coming from the side we tend to have been educated on, which is, the physical sciences, engineering, mathematics. That's what we mean by modeling there. But this is one of the cultural challenges we have with the biologists and medics. If you talk to them about a model, they actually think of an animal, because you mentioned that earlier. A model for the human heart might be a mouse model or a canine model. Before you know what you're talking about, we're at almost cross purposes here. But the message that we're coming to from this is it's certainly leading to the diminution, if not total eradication, of animal experiments, because we don't need those kind of models anymore. We just need increasingly high fidelity information about ourselves as individuals, and the outcomes of those types of simulations are much more reliable than an animal model of oneself.
In fact, let's go to a really, for us, the pinnacle of digital twin research is the human heart. And actually, I work at the Science Museum, the day job, and if you go to our engineers gallery, we've got the digital twin heart of Yasmin Aguada Sierra, who actually helped us launch the book in the Science Museum. And Yasmin's really interesting. She's an engineer. She works at the Barcelona Supercomputing Center, and she was the first engineer scientist, I think, to actually model her own heart. And in Barcelona, they've got an off-the-shelf computer model of the heart called Alia Red. In fact, even Dan Brown has popularized Alia Red in some of his pot boilers. And what you do is you take Alia Red and then you customize it with data about your own heart through various scans, whether it's the electrical activity of your heart or MRI scans of the heart. And then you can run Alia Red customized with your information, in her case, on Mare Nostrum, which is a petascale supercomputer in a beautiful deconsecrated chapel in Barcelona. So here's Yasmin's heart. And remember, this is not like a Hollywood visual effect. There are billions of equations in this. This is actually behaving like her heart. It's not just a matter of making it look pretty, although actually the Barcelona guys are brilliant at making them look photorealistic. But here's her heart beating away. I mean, Peter, I don't know whether you want to comment on I don't know how much you work with Yasmin at all.
Certainly, we do quite a lot of things together with them, and in particular, because we were talking about vasculature, we have models that are of the arteries and veins across the whole body.
We're going to come to those.
We're coming to that. But I mean, the main thing here is that this is a high fidelity representation of her heart. She was interested in what things might happen to it during pregnancy and other things. You may want to mention that.
She's tracked her. Yeah, she was pregnant. Happy sort of a mother now.
Yes.
But she tracked the changes to her heart during pregnancy, and she was also very interested in differences between male and female hearts as well. And again, another thing that Peter was alluding to is if you look at overwhelming health data, it tends to be white, it tends to be male, and it's a bit impoverished in terms of diversity. So she was trying to overcome that.
And we're going to come to collections of hearts in a minute, I think.
We are going to come to collections.
Hearts.
So here's another view of her heart. And these, basically the heart, you get a kind of a wave of electrical activation of heart cells, which makes the heart pump. And here you can see in the heart model that blue wave is showing you the wave of electrical activation as it sweeps over the heart. So if you were going to put a pacemaker in that heart, for example, Peter, you could presumably use this to check the ideal place to put the pacemaker.
That's what people do in medical device companies. They take advantage already of these personalized simulations to try to build personalized versions of pacemakers and things like that. Because clearly, what we're talking about here is regular rhythms turning into arrhythmias that might lead to what we call fibrillation and the onset of heart attacks.
This is when the heart looks like a ball of worms almost. Everything is disorganized. The individual heart cells are not pulling together in any coordinated way, and obviously it's not pumping anymore, so it's often fatal actually, if you get
indeed.
that.
So you try to be able to inject a pacemaker that will literally create a pacemaker effect for the whole set of cells in the heart.
And again, try to restore this regular rhythm. And here's another view of Yasmin's heart, and this is looking at the muscle fibers in her heart. So the great thing about these digital twin models is you can sort of, like an old anatomist, peel back various layers and show various things at work. Let's show you another view. So here, this is showing the precise blood flows through a heart, and I think each red particle is something like, is it 400,000 red blood cells or something?
It would be. They're sort of streamlines. And the whole message here is this is an immensely sophisticated model, but it's personalized. It's got the electrophysiology which drives the mechanical beating, and it's also got the blood flow in and out of the heart. So hearts are the most advanced form of organ modeling for the human body that exists today on the planet. So it's a really good example of something that's now becoming a digital twin, and we're going to talk a bit more about what happens when we amass a lot of them shortly.
Yeah, let's show you. Here's so LM is a spin-out company from the Barcelona Supercomputing Center, and there's Yasmin up there in the top corner, and they thought, well, actually, when we show ourselves online, we should show our hearts as well. So this is a digital twin customized of their individual hearts. These things, we're beginning now. Heart surgeons and medical device makers and others are beginning now to use digital twins to plan operations. And also in Oxford, there's some amazing work by Bianca Rodriguez, isn't there, going back to animal research. Peter, talk a bit about that as well.
Well, that's just doing what we said earlier, that they've been able to show that for some forms of clinical trials, unambiguously you get better prediction out of the models of this sort when you're testing drugs. You're looking at side effects like toxicological ones and so on. You get far better predictions of what's actually going to happen to individuals from these models than you would from animal models of any sort. Are we going to be able to talk about the clinical trial scenario? Because I'd quite like to say something about that now.
Yeah, we'll go for it.
So
Peter,
the thing is that this is talking about collections of hearts, but they're not statistical hearts in a sense. Each heart belongs to someone. This is part of your virtual you, as our book is called. Envision a future where you own your own data, because this topic is also going to be important. And what it means is that it's built out of your data for your image or your imaging. The model has a particular set of parameters that are those for you. And therefore, in the future, and with this group of people, every person there has their own data and their own parameters for a model of this sort. So it's possible to then start about doing clinical trials in silico. So maybe we've eradicated animals, but now we're going to minimize the risk to you as an individual because we'll do the testing on your heart, virtual heart, rather than your own one. And this is what's becoming a very compelling concept at the moment. In fact, the first time this was done by this team was when Donald Trump was previously in power. And you may remember at one stage when COVID struck, he came up with some very good suggestions. Towards the end, it was that we could take bleach and that would cure the problem. But before that, he suggested a certain set of anti-malarials that were good at this. And then the question becomes, okay, shall we test this guy because he's all-powerful and omnipotent and what he says better go? Are we going to set up a clinical trial to test his ideas? Well, believe it or not, there were 2 clinical trials where possibly a lot of Trump supporters volunteered to undertake the testing of antimalarials. But if you're smart, that's a word that Trump likes a lot, if you're a smart person, you do this in silico. And that's what this team did. They put a clinical trial together with the same sort of numbers of patients, virtual, as the real clinical trials had. And indeed, what's very interesting about that was they were able to have men and women, varying individuals, and the results of the in silico trial were very similar to
They had Democratic hearts as well as Republican ones?
Yes, all kinds. The statistics that came out of this trial were very similar for the in silico to the real one. And the point that was uncovered there was that you find, some forms of arrhythmias develop. And for men and women, because their hearts are different shapes and sizes, you get characteristically different responses. And sure enough, in the in silico trial, we were seeing those kinds of effects in the two categories, male and female. So that's the sort of thing that people are now taking very seriously. Indeed, if you think about what I was saying earlier about the paucity of the pharma's attempts to develop drugs, where today we know in a post-genomic world we're pretty different, we need more of them. Imagine if you can convolve the testing of your virtual drug with a virtual patient's relevant organs much earlier on in silico, so that you've already gone a long way to check whether these candidate drugs will work in what is traditionally the clinical trial stages, and there are 3 of those in conventional drug discovery. And the later on in those trials, normally, the more expensive the failure is when it occurs. So it's about being able to optimize all aspects of the drug as you develop it very early on in a computer, and you better have a very powerful one to deal with all of this.
In fact, talking of which, let's go to the next slide here, because this is Peter's own work. Maybe you should talk a little bit about Yoon Sun first, Peter, because this is based on real data, and then...
you tell us who she is or was.
Well, Yoon Sun is from the a Visible Human project done in South Korea. So she gave her body to medicine, and her entire body was digitized, which actually means slicing it up almost millimeter by millimeter, capturing a whole range of data, whether photographic or scans and so on. I mean, sadly, I think she died when she was 26 or something like that. And Peter was interested in extending the heart work and capturing the whole circulatory system of the body. So, Peter, you took data from Yoon Sun. I should say, of course, there's ethical approval for all this sort of thing. And then in Frontier, which is the first so-called exascale computer on the planet, so it's still the most powerful computer on the planet?
No, it's actually number 2 since
number 2
last November, yeah.
Okay, so that's your simulations now. I mean, you could imagine, in the longer run, you can couple a digital circulation to a digital heart, and the kind of things you could do would be to see how a clot moves around the body, or there might be, we always think of there's a thing called blood pressure, but of course it varies during the day and it varies throughout the body, and you can get areas where you've got abnormally high blood pressure. So Peter, tell us a bit more about how this works.
This is another one of the organ systems in the human body, and we talked about the heart. Here is the vasculature. It's the arteries and veins and how they're coupled together. We have developed a code that, fits the blood flow of the entire human body across all of that machine. This code is actually one of the very few that scales to 10,000 nodes. Each node has 8 GPUs on it. So you have 80,000
he's using
GPUs.
supercomputer jargon here. So a node is like imagine you've got a PC. That would be a processor.
Well, it'd be much more than
a
one
node
processor.
would be like 10,000 processors?
No, it would probably be of the order of, let's say, 100 or so processors,
100
maybe
processors.
200. And then it's got 8 GPUs on them, which are themselves many times the power of 100 CPUs, the processors you were referring to. So this is an incredibly powerful...
now. So GPUs, they're like, you often hear them talked about with AI, but actually they're central to these great behemoths, these computational behemoths.
So you can run the thing very quickly. But the main point to make here is just that we're building up these very accurate models, patient-specific models of different organs, like this, the heart, there's the lungs, there's the liver and other things. In different areas of the world, people are specialized in those. What we're trying to do is ensure they can interoperate with one another. And the vehicle by which they interoperate most is actually the vasculature that connects lots of this stuff together. In the fullness of time, we expect to be able to bring all of these things together on an individual basis. And at the moment, as you hinted, we do have the first stages of coupling the Alia heart model to the vasculature that's already been submitted for publication, from which we can then look at the cardiovasculature, which is incredibly important for disease and so on. And it's beginning to point at things that Western medicine normally doesn't do. Because Western medicine likes to break everything down into small parts and analyze the death out of those. But there's another side to the way we exist, and that's a more holistic one. Starts to sound spiritual, and you probably realize that
perfect for the Jaipur Literature Festival.
Yes, exactly. For these traditional medicines, there are things that do work there that people are not really sure about, but they're likely to be the result of interactions between different organ systems and crosstalk. We're only going to get to understand that when we have these more holistic models.
I think we'll take some questions in a few minutes. We just got two kind of general points to deal with. People always say, you know, what about AI? And Peter's already alluded to the fact you tend to train an AI on population data. So you're getting a one-size-fits-all medicine out of an AI model. They're quick. So once you've trained up an AI, they're much easier to run on a much smaller machine than the kind of behemoths that we've been talking about for the digital twins. So we've tried to sum up in this yin-yang thing how actually we see the future of modeling. You know, we've talked about getting equations, bringing them to life on a supercomputer, and so on. But we think in the midterm, there'll be a fusion between AI and what we call physics-based modeling, because AI is quick and it can give you some very good insights, but also it's got no common sense. It doesn't understand how the world works, unlike the physics-based model. So a kind of a synergy between the two seems to be a very powerful way forward.
It's quite ironic that you say it doesn't have any sense when it's called artificial intelligence, but that's the reality of it. So you have to create an environment where the AI has been conditioned to understand the laws of nature, for example, or it does things which we're all conversant with now, so-called hallucinations and just making mistakes because it goes off on tangents. But in general, we'd expect the convergence of these two. And indeed, in the weather forecasting area today, a lot of that is starting to happen because it can help you accelerate some of the calculations and get your answers into this actionable time frame. You have to be able to predict tomorrow's weather today. There's no use in me telling you tomorrow's weather in 3 weeks' time because it's of no interest to anyone.
In fact, I was at the Met Office a couple of weeks ago. They've now got a cloud-based supercomputer with AI. They've got something called FastNet. And the things they're playing around with, you know, with their latest supercomputer, they hope to give quite decent classical forecasts in 2 weeks' time. But with an AI module, you might have an app on your phone in a year or two where the app will say, you know, where you're standing, it's going to rain in 5 minutes. So the AI will take the physics-based model and extrapolate on a very hyper-local level what the weather might mean for you. So just think, no more leaving washing out in the rain and things like that. It's going to be revolutionary. But the idea that AI will completely replace... the other thing about AI that people don't realize is if you look under the bonnet of an AI model, there are sometimes, 1 trillion parameters, maybe millions. You don't get any what we call mechanistic insights. It gives you an answer, but you don't really understand how it got that answer. I mean, they're working on it at the moment, but it is a severe weakness
generally
of AI.
that's the case, yes.
So that's one general thing. And then the last general thing, and then we'd love to get some questions from you, is of course there are ethical consequences of digital twins. And I don't think any of these will come as a surprise. I mean, there are classic ones about data protection and so on. There are classical ones about only the rich can afford to get access to digital twins. We've said there are big pluses in terms of maybe avoiding animal experiments and so on. But I think those are probably, even with a digital twin model that isn't quite simulating reality, What it is saying to you is you don't quite understand reality, so you've got to go back to the drawing board. So I would say even a digital twin that isn't quite working properly is giving you some very important
It will never
insights.
be perfect, but in fact what we're just advocating is the use of the scientific method to
Yeah.
improve our understanding. But I would say the important thing about a personalized medicine, and I haven't used the word, but I'm foolish for not doing so in the Jaipur Literature Festival, that your own avatar is something that you should own yourself. Because one of the questions is, who's got control of this data? And it's very well known that today it might be held in a set of hospitals up and down the country, or even, heaven forbid, across multiple countries. Even worse, the big tech companies have a tendency to want to hoover this stuff up, and then you don't know what's going to happen. We're not talking about that here. I mean, you have your own avatar. You have your own access to it, just like you control your own bank account. If you're satisfied with the security on your bank account, I bet you'd be satisfied with that security operating on your avatar. For the most part, you'd rather not lose your money than someone see some part of the data in your avatar, but you can debate that. So the main thing is you control it, and then if you want to participate in an in silico trial, you agree to produce some part of what you've got and into that clinical trial. It's not controlled by other people. So it does open a lot of interesting opportunities into the future, I think.
And in fact, it might make us redefine what we mean by feeling healthy, for example, because, in a not too distant future, I can see where you might not create not just one digital twin of yourself, but maybe thousands of digital twins, each experiencing life in a different way, different exercise regimes, different drug regimes, different diet regimes. So you can work out from this population of evolving digital twins what's the best way for you to live. But it's got an interesting corollary, which is that, to give you a crude and semi-realistic example, your digital twin might say, hey, Roger, you look fine, but that 3 bottle of claret a night habit that you've got is going to knock 10 years off your life. So you might feel fine, you might look fine, but actually when you look into your possible futures with digital twins, you might find that actually you're leading quite an unhealthy lifestyle.
But we should add that you don't have to do any of this if you don't want to know, and that's already an issue in medicine. Some people don't want to be told some things which we know are going to happen to them if they have certain types of
Huntington's
genes.
disease and things like
so
that.
It's already an issue.
So I think there'll be some, people are always anxious about new technologies being rolled out, and I think like any new technology, it's a double-edged sword. You can do good things with it, you can do bad things with it, but the key thing about this is it's personalized, and that's the thing we want to keep on. It's personalized and predictive, and if there's one thing we would love to see in medicine in 10 or 20 years' time, it is that medicine becomes personalized and predictive and not one size fits all and reactive as it is at the moment. And I think that might be a good time to take some, just see how many, we've got 15 minutes. Is anyone itching to ask a question? I can see a gentleman running for the door over there. Well, I didn't mean it. Okay, one question down here.
Hi, thank you very much for that very interesting discussion. I'd heard of personalised medicine in terms of genomics and drug response to drugs, but I hadn't heard of this in terms of the digital twin. So I wanted to ask you a question about the model you showed, the physical model of risk to bone injury, risk of fractures. So I didn't really understand how it can be predictive. I mean, more than bone densitometry, for instance, in real time now, it gives you an idea of your risk of fracture. But how can it be predictive, and what data do you input, in the sense that we know that South Asians have increased osteopenia, for instance, compared to African bones, or so how do you include that diversity of data? How do you predict the future risk of fracture? Is it with things like your mobility, your exercise, as well as your bone structure? I just want to know a little bit more about that model, please.
This is really very much an engineering endeavour, and you mentioned, for example, Marco Vicciconti and others at Sheffield, who are heavily into what they call neuromuscular skeletal research. It's really applied mechanical engineering of a sort. And it uses a lot of information on the structure of the bones, which are actually pretty complicated in detail. There's a multi-scale element to this. And in the end, if you're talking about a fracture, to understand fracture of any material, it's never enough to just look at the thing macroscopically. We understand that fractures usually occur because a chemical bond breaks. That's at an incredibly short time scale. So we have to have a representation in the model of that component of the system. And then we need to know something about the regime, mechanical regime that it's subjected to, and we will benefit from having imaging data on the patient at all times. So for example, in Sheffield, they have a bunch of codes that are used to make these sorts of predictions. Fundamentally, you have to have a multi-scale model, an understanding of what the individual's state of play is from their imaging, and a capability to model and simulate that stuff accurately. But at a certain level, that's generic to all the types of virtual human and digital twins we're working with. You have to have a good data set for the individual and a good predictive model. And to emphasize again, as always in science, as we learn more about things, we improve the models. That's why the feedback between what is being predicted and what happens matters. In the end, it's got to be a virtuous circle between the two.
And I suppose, just to give you another take on that, if you do take several measurements of bone density for an individual of a certain height and certain weight, you'd hope that with this sort of model, you could predict that maybe in 6 months' time, they're in danger of crisis
Totally,
unless
yeah.
there's some action is taken.
Yeah.
Another question, please, or at the front here. Hang on for the microphone so we can...
I work in the biopharma industry, and there's a lot of conversation around the replacement of animal studies. So where do you think we are now, and what are your thoughts for what's around the corner? I think the FDA as well are looking at maybe looking at alternative studies to animal studies as well. Do you think it's realistic that digital twinning of animals would allow us to eliminate animal studies and maybe get a faster pathway to a drug approval?
Yeah, I mean, as you say, if you work in the pharma industry, you're hidebound by regulations, and bodies like the FDA dictate what we can do. Fortunately, they have traditionally been the most advanced in terms of thinking about in silico methodology. So they have already got regulations that you have to conform with if you're going to use an in silico model to make predictions. Because ultimately, this is science, the predictions that come out of some simulation can't depend on the person who did the simulation, or indeed what machine they ran it on. It has to be a protocol that's objective scientifically. So you have to be able to establish those. And anyone who's trying to develop these in silico methods has to comply with the requirements of the FDA, and then they've got a chance of something being adopted. This always takes time. And then there's this inertia about the biologists and their understanding what a model is versus what I usually think a model is, and that they have to begin to gain confidence that models that are usually the talk that are dealt with in the physical sciences and engineering do have a certified reliability to them. So this brings a lot of things into bear, like the cultural and educational components. And people will drag their feet to an extent, always say, well, I must test this on some other entity than a human. You see what we're saying here, the entity can be a virtual version of you. And there are indications and examples now where that already is established. The virtual version of you having a simulation done on it is more reliable than the animals that people have been using. But this is going to depend on which disease case you're in and which industry. You can see here we're jumping between the molecular end, which touches on genomics on the one hand, but the models with the heart and the organ systems, to a first approximation, pay no attention to genomics at all. They're dealing with other types of data completely. And in the fullness of time, all of these things do have to come together, because a molecular, we were talking about earlier, a molecular, let's say a new molecule contender that might seem to do a good action on a given target protein may end up having these negative effects on the heart. arrhythmias and so on, which are not noticed initially. But if you bring these things together in silico, you start seeing the fact that that might not be a good drug to work with. You see that much earlier. So all of this, I believe, must be pursued quite vigorously. Do you see? And then we start recognizing collectively it's no point in doing these animal trials because they're not giving us the information we thought they would.
So let's take another question just over the back there. So the key thing to take home is regulators are accepting digital twins and there are spin-out companies developing them. So it's not pie-in-the-sky sci-fi. Let's have the question.
Hi, thank you so much for your talk. It was really interesting to see the models that you showed. I'm a public health student and I'm quite interested in the access that we all have to healthcare. So my question, I guess, is do you see these models being used for every patient? So we would maybe go into a GP and have our medication tested on our digital twin before it's prescribed to us. And I guess my second part to that would be, would there be a disparity in terms of if people could afford it, they were more likely to be able to have access to this? Thank you.
Maybe Peter, because I think his experience in India just recently, I think is really
But I think
revealing,
before going to
actually.
India, the issue is, I mean, I've attended 2 or 3 meetings at the Royal Society of Medicine which are about inequalities due to digital health, and you're sort of alluding to those there, in the NHS in the UK, because the NHS is supposed to be free for everyone at the point of demand and requirement. But of course, to get onto the digital health, you need to have a mobile phone for a start, and you need to potentially access a computer in order to even find out what the services are. And there's something like of the order of between 15 and 20% of the population in this country that don't have access to mobile phones, and they don't know what their rights are. So they're already at a disadvantage. But that's what you're getting to. The amazing thing about India is that in India, everybody has a mobile phone. Everybody, by design. This is the most populous country in the world, and everyone has a mobile phone. So you're, in India, at a much better state, potentially, to implement this stuff. Because without a mobile phone, you can't even find out what your rights are. If you have one, then you start to be able to interact with the system very easily. And do you remember I was talking about you have your avatar there, you can access it through a mobile phone. If you don't have that, you're at a disadvantage. So that's what I'm saying is a good thing about having access to mobile phones. Ironically, if you like, India is in a much more interesting position than the UK in that respect.
I think the UK, was it 15% of the population doesn't have a mobile
or
something?
Something like that,
which is rather startling. I think we've got time for maybe 2 more questions. Anyone else want to push us about? There's a lot of people who've come in who haven't heard the talk, probably thinking, what on earth are these guys rambling on about? We're talking about making digital copies of you and using it to develop personalized and predictive medicine. Look, here we are, brave soul over here is going to ask a question. Maybe we'll make this the final question, so it better be a good one, okay? No pressure.
No pressure, okay. I'm just interested, has there been any modeling done on the microbiome of a person which are already
on the microbiome,
known
okay.
to be personalized?
So this is microbiome, so basically you've got as many cells in your guts as you have in the rest of your body, and you can almost look at human beings as 2-legged bioreactors, and your microbial passengers are playing an enormous role, not just in food digestion, but even in mood and things like that. So, Peter, I think there are attempts to come up with virtual
definitely. Digital twins of the microbiome are already being mooted, if not actively pursued.
I seem to remember that there's a very diverse group of digital twin models of the body in New Zealand, isn't there, in the Auckland Centre?
Yeah, they have a lot of different things going on there.
So I think even a microbiome, it's a great question actually. So it could be that could give you a bit of insight into mood. And of course, one thing I suppose we should make clear is that, that we've talked a bit about simulating your future, but a true digital twin will be taking information from your body the whole time and using that to inform the twin and vice versa. And it could be that with information from, say, your mobile phone, you can pick up some insights into mood. I do remember meeting the head of Nokia Research once, who claimed that the accelerometers in your phone, he could tell how much of a spring in a step you had as you walked down the street, so they could use population data and see whether the population were broadly happy or a bit grumpy and a bit down in the dumps. So there's lots of interesting data sets you can mash up with these kind of pure physiological ones.
Totally, yeah.
Well, I think we've probably comprehensively blown your minds now with digital twin research. So thank you for those brilliant questions. Thank you to the JLF organisers. It's always absolutely fantastic to be at the JLF. And have a wonderful festival. Thank you.
Thank you.